a lot of notes for today, so we'll see what happens. Well, it doesn't necessarily take a lot of notes for me to fill up 35 minutes. Okay, so starting today, we're looking at well-posedness. What does it mean for a problem to even be attempted to be solved? I know that grammar was awful, but so, because there's some PDEs, it's pretty easy to write down a PDE that really is no point in trying to solve, certainly not numerically, and numerical methods would fail for it just because the behavior of solution would just be, it would, it would behave in an unstable manner. Having solutions that grow exponentially over time, things like that. So a lot of the theory behind either numerical methods or analytical methods about behavior of solutions relies on the problem being well posed in the first place. And what does it mean for a problem to be well posed? There are three conditions. And although these conditions were originally stated for problems involving PDEs and associated initial boundary conditions, these are very generic concepts that could be applied to other types of problems as well. So, let's say a problem, and by a problem I mean PDE plus whatever boundary conditions we have, which if it is a boundary corresponding to time could be an initial condition, is said to be well posed if first must have an existence of a solution. Okay. Also, that solution must be unique. If you have non-uniqueness, then that means that there's some other condition that you ought to impose to have a unique solution. And then, following the solution depends continuously on the data. Where data is defined broadly. So in the case of a PDE, could refer to coefficients, for instance, or boundary data, like what if you have an initial condition? So that would qualify as data for a problem as a whole. Now, the way I like to think about this third condition, solution depending continuous on the data, is this. So another way of phrasing it is, if you have a small change in the problem data that does not lead to a large change in the solution. Now, there's a name for this concept in specific to numerical methods. We would have covered this back in Math 460-560. It's called well-conditioned. So a problem is well-conditioned if the output of the solution of a problem is relatively insensitive to the problem's data. We don't want to have a situation where a slight change in the problem data could cause a large change in the solution. And when you're dealing with numerical methods, especially, because that would mean that you can't trust your solution at all. Reason being that you will always have changes in your data. You can't count on your data being exact in numerical analysis. There's going to be error of some kind, rounding error, like whatever input you have into a problem is generally not going to be exact, especially like what if that data comes from measurements, which naturally are going to have some error. And if something as small as measurement error could throw off a solution by a lot, then why solve a problem? I mean, you might as well guess that's what the solution is. So having well-posedness is important for purely analytical reasons too. And these conditions were formulated for analysis of PDEs, but they take on, this third condition takes on greater importance when it comes to numerical methods. All right. And it turns out though that variations of the same problem can cause any one of these conditions to fail. That can take you from a well-posed problem to an ill-posed one. Okay. Now, let's see. So I'm going to give some examples of problems that are either well or ill-posed. So let's suppose our PDE is just UXX plus U is equal to 0. Now, I'm not going to specify boundary conditions yet, but the general solution is just a linear combination of cosine and sine. So you would choose your constants A and B to satisfy whatever boundary conditions you have. Okay. Let's look at different boundary conditions. First one is 0 equals 0, which if you substitute x equals 0 in here, that immediately tells you there's not going to be a cosine term. Because a cosine of 0 being 1. And then let u of pi over 2 equal to 1. So this is a well-posed problem. And it has a unique solution. It's just sine x. So if you were to set x equals 0 and x equals pi over 2 in here, go ahead and do that. All right, so we get a times cosine of 0, which is 1, plus sine of 0 is 0, so you get nothing. That equals 0. And then for x equals pi over 2, you have a times cosine of pi over 2, which is 0, plus b times sine pi over 2, which is 1. That's equal to 1. So sure enough, you have this trivial system of two linear equations and two unknowns. That get if you a equals 0 and b equals 1, so you get sine x. So so for a problem like this, wherever you have a solution at all, or unique solution, or infinitely many solutions, it becomes a linear algebra problem when it comes to the boundary conditions, because two boundary conditions you have give you a system of two linear equations and two unknowns, and that system can have none, one, or infinitely many solutions. Okay. Let's suppose I have u of 0 that equals 0 again, and then u of pi is equal to 1. So if we take a look at that, the system of linear equations. Okay, so to substitute x equals 0, you get a plus, and then you get 0 over here, and that's 0. All right. And if for x equals pi, well, cosine of pi is -1, so you're going to get minus a. And then sine of pi is 0, so you get 0 over here. And that equals 1. Well, this system of linear equations is, well, what do we call when a system of linear equations looks like this, in this kind of situation, what's that called? That's from your linear algebra class. Inconsistent. This is an inconsistent system of equations. There's no solution because there's no value of a, b that will satisfy both these equations. So the first condition for well-posedness fails, that we don't have existence of a solution. So the PDE was fine, but the boundary condition was bad. We have one more. Okay, u of 0 is 0 again. Then u of pi is equal to 0. So now we have the same equation for x equals 0. And then for x equals pi, yeah, cosine of pi is -1. And then we get 0. Okay, but the matrix is the same. Then we have 0 on the right-hand side. Okay. So what does this tell us about what kind of solution we have? In terms of existence or uniqueness or... Yeah, there are infinitely many solutions because a has to be 0, so there's no cosine term. But these conditions, these equations, did not constrain b in any way. B is allowed to be anything. So u of x, so b sine x. So we have existence, but we do not have uniqueness. So these are some things that can happen. The PDE, depending on the boundary conditions you have, you might not get a solution, or you might have infinitely many solutions. So questions about this example? Okay, but so far I've only given examples for existence and uniqueness. What about the other condition? Continuous dependence on theta. Okay. So two very similar problems. One is well posed, one is ill posed. So we have. So this first problem, root p equals uxx. This recognizes the heat equation. And then I'll specify boundary conditions. For x equals 0, x equals 1, solution is equal to 0. So those are boundary conditions. And then we'll specify some initial data. Of x, so that is the initial condition. And this is a problem that is well posed. And in fact, I can write down a formula for a solution in this case. It's something we would have picked up in a first PDE course, like using separation variables. So u of xt is sum k e to the minus p sine k pi x. Okay, going from 1 to infinity, where the constants uk hat come from a Fourier sine x, Fourier sine series of your initial data of x. Okay, so and here we have this exponential decay happening over time. So because we have a solution formula, that right there gives you existence and uniqueness. But I'll talk about continuous dependence on the data momentarily. Okay, now, second problem, ut is equal to minus uxx. That is backward. The equation. And then we have same boundary conditions, same initial condition. So nothing about the problem has changed except this minus here. I can again write down the solution formula. For sine series coefficients, but e to the plus k squared t. So that's the only change. Okay. And this problem is ill-posed. And it's because we have exponential growth here over time, as opposed to exponential decay. So in terms of the actual condition, Hadamard's condition, small change in the problem, preferably not causing a large change in the solution. If I were to change UK hat a little bit, even if just for one coefficient, this is not going to change very much because what is this coefficient amplified by in the solution? Sine k pi x, which is between -1 and 1. So it's not going to grow in magnitude. And then times the decaying exponential, e to the minus k squared t. So in fact, over time, the solution is going to be, this solution is going to 0 as t goes to infinity. So in the long run, whatever change you make in the initial data doesn't change anything at all. Okay, on the other hand, here, make a slight change in some coefficient UK hat, that is amplified by e to the k squared t, and this grows without bound. So the slightest change at t equals 0 results in a change as large as you can imagine, actually larger, eventually as t goes to infinity. And that's it. I mean, if the solution over the entire domain, I mean, the domain of this problem is x between 0 and pi, and sorry, x between 0 and 1. And all time from t all t greater than 0. Now, if we were restricting ourselves to a bounded domain in time, well, actually, that still won't help, because you have these for k going from 1 to infinity, that
Stays the same.
yeah, it's still going to, well, I mean, at least you can have some containment. So, what we like to be able to quantify how much a solution changes, but here our solution is a function of it, x and t. So to try to get a handle on how much of a magnitude of a function, we use what are called norms. So in other classes, you may have seen, vector norms or matrix norms. So here we're talking about the norm of a function that has an analogous definition. So I'm going to, okay. Actually, I wasn't going to get it to that, but I think I will. I don't think I'll fall behind. I'm already behind in my upper class. But, okay, first, any questions up to this point with these problems? All right. Okay. Still within this example, use norms. We'll see how much the solution changes in terms of a change in initial data. Norms can help us do that. Now, there are different norms we can use. So what I will use, okay, so in general, we use let's call it LP norm, where P is a parameter to be specified. And that is defined as an integral over some domains. That domain has to be specified. That's valuable x raised to the p power, whatever p is, and then raise that to the 1 over p. Often the L2 norm is used, so you integrate the square and then take a square root. Just like the magnitude of a vector, you're accustomed to like the Euclidean length, square root of the sum of squares of the components. It's just the same idea. So p could be 1, 2, or even infinity is of interest, where the L infinity norm is you're taking the maximum absolute value of your function on the entire domain. So, for the heat equation problem that I was just discussing, I'm going to use p equals 2, and my domain will be the interval 0 to 1, or spatial domain of the PDE. So, we use a 2 norm. I want to say my notation here. This is actually common notation. You may have seen this before elsewhere. Is u is a function of x and t, but I'm taking a norm as the integral with respect to x. So the result of that will be a function of t. The dot here is used as a placeholder, because if I put an x here, that'll make you think that this whole expression is a function of x, which it's not. So that would be integral from 0 to 1. Value to the 1/2. Now, what? Okay. And the reason why I could use all kinds of norms, but I'm using the L2 norm in this case because of this convenience. Well, Parsifal's identity. Actually, I need to make sure my scaling constant is correct. Okay. Oh, actually, I think it's easier to handle since it's from 0 to 1 to 0 to 2 pi. So it turns out that the L2 norm squared is equal to the sum is 1 to infinity of UK hats. And then we have, really, it's a Fourier coefficient. Now, UK hat is actually a Fourier sine coefficient, not of U of xt, but of the initial data. So we had to include the exponential part. That's part of the Fourier coefficient. So the UK hat is from initial data only. To get the Fourier series coefficient of U of xt, we must include this factor. This has to be squared. The partial identity relates the norm of a function of x to the Fourier series coefficient. Now, I want to emphasize that I need to give a disclaimer because I am doing this impromptu. I'm probably missing some scaling factor here, which isn't really central to my point, but I'm just letting you know that this, okay, so I'm going to do this. I'm going to put, in the interest of preserving some rigor, there, say it's proportional to. So it's that time some unknown scaling constant, and maybe if I have time, I'll figure out what it is later. Okay, now, so let's suppose if this data were to change a little bit, but actually, the point is, I can say that this is strictly less than the norm of the solution at t equals 0. Because this norm at t equals 0 is equal to this again without the exponential, because you'd be plugging in t equals 0. So this helps ensure that the solution cannot change all that much, because the magnitude of the solution is dwindling over time. It actually, it's exponential, so it goes to 0 fairly rapidly. So in the case of a forward regular heat equation, you have this. But what would happen to this relationship in the case of a backward heat equation? What would be different?
The exponent with positive.
Yeah, and what does that mean about this statement here? What would happen?
Grow but larger.
Yeah, the magnitude solution is going to grow over time. In fact, if I let the initial data change to itself plus some perturbation, so like epsilon of x, then the new solution minus the original solution that is proportional to, because everything is linear here, that should be an epsilon. Okay. So this quantifies how much the solution changes. At, oh, whoops, sorry, the t should be part of the exponent, not sure what I was thinking there. A squared t. And this goes to 0 as t increases. So that shows that a change in the initial data does not mess things up too much. In fact, so like I said, eventually there's no effect in the solution. Whereas if I change this to a plus, the change in the solution goes to infinity as t increases. So
I don't get the part where t going to infinity will not cause, because if t goes to infinity, the term e to the power negative k squared t, does it not grow?
the e to the minus k squared t goes to 0.
Okay, so
Yeah, decaying exponential will wipe this out. So for forward heat equation, backward heat equation, this minus is not here, it's gonna go off to infinity.
And that is bounded, right? The term before that, u dot 0,
Oh, wait,
before that?
oh, that?
Yes, that's bounded, right?
Oh, yeah, well, because you have whatever initial data, that's just some function
Oh.
that you take its norm of. Yeah, because it's that, or so it's that. When t equals 0.
Thinking, if we're thinking about the exponent, then it should be bounded at 1.
Oh, wait,
If you have anything, if we have e of the power 0, then it's sort of just
oh,
constant.
yeah, okay, all right. Yeah, because here I was thinking about t being strictly positive. Yeah, okay. But since I didn't write that. Okay, cool. All right, questions about any of this? And anything I've written here deals with the heat equation. But if it was a backward heat equation, yeah, you drop the minuses and then all this becomes false. Okay. Oh, I just realized that in my notes here, I have these solution formulas for the two heat equations. And yeah, they do match, except totally forgot the initial data. They were not included in the solution formula, so now I gotta fix that in the notes. Okay. All right. All right. Okay. I think I already said, if there are questions about anything we have here before we move on from well-posedness. So in fact, last time I mentioned a variation of heat equation, the Perron-Malik equation for image processing, where you have a coefficient that can be positive or negative. And so because of where it's positive at all, that PDE is ill-posed. But strangely, it can still be solved numerically. But one of my colleagues, UC Irvine, came up with a variation of Perron-Malik equation that can be proven to be well-posed. So it's normally when you have a problem that's ill-posed, it's like, oh, forget it, don't bother solving it. But once in a while, there could be an exception. I guess this is very informal, but if your problem is just a little bit ill-posed, then maybe you can still do something with it. Okay. Next, we have notions of solutions. Now, another thing, oh, well, something's a solution to a problem if you can just substitute it in and it satisfies it. Well, that is most of the story in this case, but we do need to go a little bit beyond that. Okay, so first we need to define this. So c to k, this is actually not an exponent. That's one thing that as you go to higher level math, regression math, that students have to keep in mind, that oftentimes where superscripts are used that do not refer to exponents. Um, this refers to a function space. All functions with at least k continuous derivatives. Okay. So C2 is based of all functions that are at least twice continuously differentiable. Okay. Now, so then a function u is called a classical solution of a PDE of order k. And keep in mind from last time, the order of a PDE is the highest order of differentiation that occurs within the PDE. So this is a classical solution if it satisfies PDE naturally, and you must have k continuous derivatives. Right. If it is a solution, but does have PDE, but is not in CK, so falls short in terms of continuity derivatives, then we say it is a weak solution. So sometimes when you have PDEs that have like discontinuities in their definition, like discontinuous coefficients, it may well be that you can't find a classical solution, but maybe you can still find a weak solution that's still of some use to you. Some numerical methods are based entirely on the task of finding a weak solution, which in some cases may still turn out to be classical, but it's not something that you can count on. All right. A couple of examples. Laplace's equation. Any solution you can find of Laplace's equation is a classical solution because it's actually infinitely smooth. So it's a property that such solutions have. The solution of Laplace's equation, we'll get into this more later, it's called a harmonic function. So all harmonic functions are known to be infinitely smooth. Okay. Another example, a one-way wave equation, this came up last time. Ut plus x is equal to 0. And then if its initial data belongs to C1, so your initial data has at least one continuous derivative with respect to x, then actually I'm going to give u of x now a name, zero name it, called f of x. That's in C1. So what happens in this case is u of xt is known to be f of x minus t. So because f of x is in C1, f of x minus t, therefore u of xt is also in C1. And because the PDE has only first derivatives in it, so it's a PDE of order 1, this is also a classical solution. Whereas if the initial data f of x was merely continuous, like for example, suppose it's the absolute value function. So it's continuous, but is not continuously differentiable everywhere. That would be an example of a weak solution. So it still fits its solution formula, but because you're not able to take the derivative with respect to x everywhere, there's one point at which you can't. That rules it out as being a classical solution. It must be weak. So go ahead and write that down. So if f is in C0, or what if it has a discontinuity? So it's not even a continuous function. Again, it would be a weak solution. Okay. Questions on these examples? All right. Okay, actually, I only have one more example to go through, but actually, remember when I did this last year, I messed something up. So I won't do that again, but this one may take some time, nonetheless. Okay. All right, so here we have PDE. So you take the u dx, multiply it by the coefficient b of x, and then take derivative of all of that with respect to x. And that equals 0. But the coefficient b of x, well, first I'll specify boundary conditions. B of 0 is 0, u of 1, 1. And then the coefficient b of x, this continuity, b of x is equal to 1. But this is on the interval 0 to 1. So it's equal to 1 for x less than a half, and it's equal to 2 otherwise. Okay. Okay. So, what's going to happen is we're actually going to come up with a solution of this thing by integrating with respect to x. So, so if I take this, if I integrate both sides of this, well, integrating once, I'm going to have b of x du dx is equal to some constant that I will call C1 for x less than 1/2. And then I integrate it the other side, and that'd be equal to some other constant C2. And because I'm considering each piece separately, b of x is equal to 1 on this over here, and it's equal to 2 over here. All right. Okay. So then what I could do is integrate again. So I'll have u of x is equal to c1x plus another constant I'll call c3. And then we have 2u of x is c2x plus c4, again, in respective domains. Although what I'm going to do here, this may seem wrong, but I'm actually going to drop the 2 in this case. And can anyone tell me why technically it's okay to do that?
Constants.
Yeah, what is it about those constants that makes it okay?
They're not same.
Yeah, but it's saying that also we don't know what they are yet. They're arbitrary at this point because we haven't imposed the boundary conditions on them yet. Okay, so yeah, so basically I've taken the 2 and folded it into the C2 and C4.
I just have one little
Yeah,
question.
yeah.
When we're integrating, we're starting with the first condition, right?
Wait.
We're starting with the given bx ux.
Yeah, I'm including this right away.
Right.
Yeah, and that's what led to this.
Yeah.
All right.
Because I was confused because of the 0.
Oh. Get some of
The very first one.
this one? Oh, okay. Oh, but integrating against it gives you these
Yeah,
constants.
that's all.
Okay, all right. Okay, so, okay. So now I got all these conditions to satisfy. I got to satisfy boundary conditions to also make sure that U at least is continuous. And I'm also going to require that this right here, b of x ux, that must be continuous. Why? Because I'm taking the derivative of it. And anything to take a derivative at the very minimum must be continuous. Because now, continuous does not mean differentiable. However, not continuous does mean not differentiable. So, yes, we got to be careful about that. Yeah, because a function that's differentiable is continuous. Okay, so from the forcing the boundary conditions, so I'll set x equals 0 for the first piece. So u of 0, which is supposed to be 0, is equal to C3. So that tells me that C3 is equal to 0. All right, so I have that right off the bat. And then for the other boundary condition, u of 1, which is supposed to be equal to 1, I substitute x equals 1 into this piece. That's the only one that applies at x equals 1. That's going to give me C2 plus C4. So that doesn't determine either C2 or C4 individually, but I know their sum must be equal to 1. Okay, so at least we made progress towards nailing this down. The next thing I have to do is make sure that U is continuous at x equals 1/2. So I'm going to plug in x equals 1/2 into both pieces. So for the first piece, I'm going to get 1/2 C1, and then C3 is known to be 0, so I'm not going to include that. And then for the other piece, I have 1/2 C2 plus C4. So these must be equal to have continuity. Okay. Now, with C3 already determined, I still need to determine C1, C2, C4. I have 3 unknowns. I need 3 equations to nail them down. Right now, I only have 2. Okay. Now, So what I can do is I can take this equation and use the fact that C2 plus C4 is equal to 1. So I've eliminated C4 from this equation. And won't go through all the algebra here. But what we end up with is C1 plus C2 must be equal to 2. Okay. Now, what's left is, as I mentioned earlier, I need b of x ux to be continuous. All right, so right here, this is from u is continuous. Now I need bux continuous. So b of x ux is equal to what? Well, I take the derivative of what we have here, which is C1, and then multiplied by B, which is 1 in the first piece. So it's equal to C1 for x less than a half. Then for a second piece, I take a derivative of this, which is C2, multiplied by B of x, which is 2. So I have 2C2. So now these two must equal. C1 or minus 2C2 equals 0. So now I have this system of equations, two equations and two unknowns, C1 and C2. I can go ahead and solve that. It'll have a unique solution. Once I get C1 and C2, I then go to that equation to get myself C4, and then I'm done. I have everything. What I end up getting for my values is C1 is equal to 4/3. C2 is equal to 2/3. So now I can write down my solution that satisfies all those conditions. So it's equal to 4/3 x for first piece, and then 2/3 x plus 1/3 second piece. Okay. So, given that the PDE is order 2, is this solution classical or weak?
Stuck. Instead get the BUX continuous. I don't know where the get there.
Where this came from? Oh, take a derivative of these.
Oh.
And we get C1 for C2. But that's multiplied by B, multiplied by the appropriate value.
Okay.
Yeah. And we require that these equal. Okay. So to be a classical solution, for second order PDE must have at least two continuous derivatives. Do we have that here? So you go ahead and take the derivatives and see if they match across the boundary. Now, it is continuous. We made sure that at least, so u is at least in C0. It is a continuous function, but what about the derivatives? Anyone?
I didn't hear,
What?
I didn't hear the
Okay.
question.
Does this have a derivative, first and second derivatives that are continuous on the entire domain?
Domain of 0 to,
Yeah, because, yeah, what goes wrong? Anyone? You're saying no, but why?
Was if you take the derivative of the first
Yeah.
and the second, you compare, they're not the same.
Yeah, they don't match. Yeah, because the derivatives will be constant functions.
Mhm.
And so u prime is not continuous. Has a kink at, or there's a jump at 1/2. So this, the u of x itself has a kink in the graph. So u is in C0, not in C1. That alone is enough to make it a weak solution. So once one derivative fails to be continuous, if the order of that derivative is less than or equal to the order of a PDE, that's a weak solution. So if you have a function that is, C2, for instance, suppose its third derivative has a discontinuity in it, so it's only in C2, but you have a second order PDE, it's still okay, it's still a classical solution. But here, it fell short, dang it. Oh, there's my water over there. It's very useful. Okay, so, and the problem is, the solution needed to have enough continuous derivatives, but it also needed this to be continuous too, because we're taking a derivative of this whole thing with respect to x just to be able to substitute into the PDE and have everything work. Okay. Okay. So questions about what happened here? Now, this is something that actually came up when taught this last year. I'm going to propose another possible solution. U of x equal to x. Now, this function here, because it's just a polynomial, that's C infinity, so that is good. But can anyone tell me why, even though this is C infinity, infinitely smooth, how come I cannot call this a classical solution of this PDE? Because this also satisfies the boundary conditions. U of 0 is 0, U of 1 is 1. So, since C infinity satisfies the boundary conditions, how come it is still not a classical solution? If you go back to definition of classical solution, what needs to be satisfied to be able to call it that?
The order,
No.
because it says kth order PDE is a classical solution if U belongs to CK.
Okay, but just a natural inclusion though, if a function is C3, it's also C2 and so forth. So anything in C infinity is C any.
1, 2, 3.
Yeah. So besides having the right amount of continuity, what other condition does a classical solution need to satisfy? So derivatives are not a problem, so we must look elsewhere. However improbable that may seem.
Should satisfy the PDE.
Okay, and how come it actually doesn't? It might seem that it does, but what's the
You said
problem?
something earlier because you said order of PD is the highest order of differentiation.
Yeah,
Is it related to that?
no,
And I'm thinking no.
okay,
I will keep thinking.
okay. What happens when you take this and plug it into a PDE?
It doesn't satisfy.
Why not?
If I differentiate this, I'm going to get 1.
Yes.
But according to the PDE, it's 0.
Well, okay, so plug in 1 here, but we have this. Another differentiation. And what do we have in here?
PDE is a function of x.
Okay,
Yeah, so if I differentiate that, I'm not going to get 0. We are going to get a constant.
well, but b of x is this. So,
Are solutions not unique in that case?
no, that's not the issue, but. So at least on each subdomain, once I multiply this by du dx, which is 1, okay, yeah, then I'll have exactly this. I'm taking derivative of b of x with respect to x. But what's wrong with that? What goes wrong when I do that? So it almost works. So if a function is equal to 1 part, and 2 another part, and you take the derivative. What's the problem with doing that?
Could you repeat that?
All right, so you have a function that's equal to 1 in one part of the domain, 2 in another part of the domain. You want to take the derivative. What?
So you're going to get 2 different
Yes,
results.
but everything is fine except that x equals 1/2. Cannot take the derivative there at all. So if this had been just a plain old constant, same constant throughout the domain, then yes, we would have a classical solution.
So we see a jump when it reaches
Yeah.
that.
Yeah, so because what you have in here, the PDE requires you to take the derivative of it, but it's something that is not everywhere differentiable. So that's a deal breaker. So it is, you cannot call it a classical solution, even though it's the infinity, even though it satisfies boundary conditions, even though it does satisfy this almost everywhere. But it needs to be everywhere. So being classical is that picky. That's what the point of this example is, to reinforce that.
Do we need it to be like a smooth
Yes,
redemption?
yeah. Yeah, and the thing is, weak solutions can still be of value. I mean, and for some problems, maybe that's all you have. It's still worthwhile to compute them. But as long as we're careful, because you don't want to be applying theory to weak solutions that's only meant to be applicable to classical solutions. Okay. All right. So, I wouldn't expect to spend too much time talking about what it means to be a solution. But when it comes to PDE, there's more to it than for other problems, because of continuity considerations. So, any last questions about classical versus weak solutions. Alright, oh,
I
wait,
might be going ahead of myself,
okay.
but like if we are thinking about exams, would we fix a goal on finding the solution in some way? Or are we going to do that in
Um,
lab?
Yeah, we'll come, later we'll come to numerical methods and how to use solutions that way. Um, And actually, what little I've covered up to this point, well, trying to think of things that I would ask about, like on an oral final exam. I guess probably the only thing I would, well, okay, auto march conditions, classical versus weak, like what do they mean? I could see asking about that, but we're likely to focus on numerical things, but I'll be more concrete about that later. Yes.
Okay, so in this example, our solution is independent of t.
Oh, yeah,
That's fine.
it's totally a time independent problem. Yeah, we only have one independent variable here, x.
So I'm thinking, what if our solution depends?
Okay, so really what would happen in that case is you have like a one parameter family of solutions. Although this problem has a unique solution. So there isn't any mechanism for it to depend on something else. Like, you know, because there are certain PDEs where you can express a solution as like, in terms of arbitrary functions of x or t. Like, okay, one such PDE is this. I have uxt is equal to 0. The general solution is a sum of a function of x and a function of t. But then you'd have to specify these using like whatever, in this case, initial or boundary conditions to nail those down. In fact, that's how the fundamental solution of a wave equation in one dimension is obtained by making the PDE even depends on x and t, but then you make a change of variable to get a different PDE, different variables of this form. And then we have a solution and we work with that. So what you're talking about is, in that case, when you have an extra variable like that, that'd be a case where a problem is not completely specified, or maybe if you have an extra variable t, maybe your initial or boundary conditions depend on that variable. But then as far as judging classical versus weak solution, that would only be in terms of like derivatives with respect to x. So you wouldn't have derivatives with respect to t in a problem like that. For a question? Okay, well, still not time yet.